First, I just wanted to say thanks to the organizers for inviting me here to talk to the ATPESC audience and give this talk. My name is Tom Papatheodore. I'm a HPC engineer in the System Acceptance and User Environment Group at the OLCF in Oak Ridge, Tennessee. And I'm going to talk about the Summit and Frontier supercomputers. So first, I wanted to just point out who we are, in addition to what Vitaly's already pointed out. So we are, as the OLCF, we are one of the Department of Energy Office of Science user facilities for computation, along with the ALCF here in Illinois and NERSC in California. And together we provide some of the world's most computational, powerful computational tools for open science. Access is free to researchers who publish. Actually take this up. And we'll see in the next slide that although it's free, there is a very competitive allocation program. So we are also what's called a leadership computing facility, if you're not familiar, along with the ALCF. And so our mission is to provide some of the computational tools for some of the most challenging problems for the scientific community. There's two data centers, so the ALCF and the OLCF, and so we have these separate architectures, as Vitaly pointed out, to address diverse needs from the computational community. The allocations on these systems are given mostly through Insight and ALCC awards. That's where most of the time on these systems comes from. And these projects are 10 to 100 times more resources than you can typically get at other computing facilities. And in addition, down here, this bottom point, we embed either a liaison at OLCF or a catalyst to ALCF into these teams that are awarded time on the systems. That way they can help, you have this direct line of communication with the centers, and you also have the ability to collaborate as well with the teams. This slide shows our path from petascale to exascale. So Jaguar was our first petascale system. So Jaguar was a CPU-only system, peak performance of 2.3 petaflops, and had a power envelope of 7 megawatts. Titan, this was our first hybrid CPU-GPU system. So this was #1 on the top 500 list in 2012 with 27 petaflops and 9 megawatts of provisioned power. Summit is our current production supercomputer. So that's 200 petaflops. This is also a hybrid CPU-GPU system. But this has, instead of just one CPU and one GPU per node, like we had on Titan, it has 2 CPUs and 6 GPUs on each node. And Frontier currently sits atop the top 500 list with 2 exaflop peak performance. It's a hybrid system, CPUs and GPUs. These are AMD CPUs and GPUs. And it has a provisioned power of 29 megawatts. We'll look at these last 2 systems in more detail. Right, so Summit currently is in the #4 position on that same list. And we'll look at that system here. So this is an IBM supercomputer. This has IBM CPUs and NVIDIA GPUs. Has a 4,680 compute nodes that are connected with dual-port Mellanox InfiniBand network, and that's arranged in a non-blocking fat tree. It mounts a 250 petabyte IBM file system, and that allows you to transfer data at speeds of up to 2.5 terabytes per second, and that's aggregate speed, of course, to the file system. The system has about 200 petaflops of peak performance, and that's in double precision floating point operations. And so that's for your traditional modeling and simulation. And a peak of 3.3 exa operations in half precision. And so that's for data analytics and artificial intelligence. Each node, as we'll see, has 2 IBM Power 9 processors. So these are 22 physical cores each. 6 NVIDIA V100 GPUs. Has 608 gigabytes of fast memory. So that's the DRAM as well as the HBM memory. and a 1.6 terabyte SSD is on each node for node local storage. In addition to holding the top position on the top 500 list from June of 2018 to June of 22, we were also awarded with the HPCG award and the Green 500 as well. So this is a schematic of a Summit node. So I mentioned some of these components before, right? So here we have our 2 Power 9 CPUs, and we have our 6 V100 GPUs, so 3 here and 3 here. And as you can see, this is sort of a mirror image on both sides of this schematic, and those represent the 2 sockets. So I'm going to actually just close off one side, and we'll focus over on just one to make it easier to look at. So this is our Power 9 CPU. It has access to 256 gigabytes of DDR4 memory, which it can access at speeds of up to 170 gigabytes per second. You can see the 3 GPUs here. Each of those is about 7.5 teraflops of peak performance in double precision. And each has 16 gigabytes of high bandwidth memory that GPU can access at speeds of up to 900 gigabytes per second. All of the processors on this socket, so the Power 9 CPU and the GPUs, are all connected with these green arrows, and that represents NVIDIA's NVLink. And so any 2 of these processors can communicate at speeds of up to 50 gigabytes per second, and that's in both directions simultaneously. So 100 gigabytes per second bidirectional, but only 50 in any one direction at a time. So you can see here, and I might point something out to do with this later, but you have these 3 links coming into this Power 9. So you have 150 gigabytes per second, which allows you to then drive this 170 gigabyte bandwidth to the DRAM on this socket. If we go back up and get rid of that block there, we can see that if you were to try to reach into the other socket's DRAM, which you can do, you can get bottlenecked by the 64 gigabyte X bus from IBM. I'm not going to cover the other side since it's the same. I will point out that we have this, this is the network card, so this is how you communicate out to the rest of the nodes. So you can communicate between nodes at speeds of up to 25 gigabytes per second. Yes?
That NV link is just to those 3, right? It's not both sides. You can't all 6 at 50.
No. No, I mean, you can traverse the X bus if you want to here to get to it, but yeah, so you'd have to make a hop through the CPU anyways. Right, anything else here? I guess this is the SSD that I mentioned, that 1.6 terabyte. So you can use that for node local storage, and that's something that some of the machine learning teams found was helpful to sort of first populate that with their some of their data or even some of the packages to be able to speed up their calculations. This is just sort of a cartoon blown up view of the CPUs. I mentioned these are 22 core CPUs. You'll notice that there's only 21 cores here on each of these, and that's because the final core here is on each of these Power 9s is reserved for system tasks. So for the user, you basically have 2 21 core CPUs. And you can see they're labeled, right? So 0 through 20, so there's 21 physical cores, which are these blue boxes. And then in parentheses, you can see the hardware thread IDs. So there's 4 hardware threads per physical core. Otherwise, there's nothing new on this slide to mention. This is an actual picture of one of the Summit nodes, so you can see some of the components we talked about. So this is one of the Power 9 CPUs with a cold plate on top of it. These are the DRAM here, these DIMM sticks. Here's another Power 9 and its DIMMs. Here's a bank of 3 GPUs, another bank of 3 GPUs. And these black hoses that come in and sort of get routed through this node, that's for the water cooling, so it runs through those copper cold plates that you see on the top, and cools the CPUs and the GPUs. Okay, and now we'll move on and we'll talk about the Frontier supercomputer. So this is currently still in the acceptance period right now, but it's slated to open to the user programs like ALCC and Insight that I mentioned. Well, Insight anyway starts in January of 23, so that's when this will first be available to the user programs. So this system I mentioned is 2 exaflops of peak performance. There are 9,408 compute nodes in the system, and those are packed into 74 compute racks, like you see here. It has a provision power of 29 megawatts. There's 9.2 petabytes of memory on the system, so that's the fast memory. And in this case, it's evenly split between the CPUs and the GPUs. So you know, you have 4.6 petabytes of HBM and 4.6 petabytes of DDR4. So the nodes are connected with a Cray slingshot network, and that's arranged in a dragonfly topology. There's 37 petabytes of node local storage, so that's SSDs that we'll see on the next slide. 716 petabyte center-wide file system will eventually be mounted on the system. Currently, it's still mounting our GPFS Alpine. And right, so it's a 4,000 square foot footprint, which is on par with some of our previous systems. So this is a diagram of one of the frontier compute nodes. It's a lot to look at, so I'll do my best to explain what's going on here. Before doing that, though, I'd just like to point your attention down here to this key. So these MI250X accelerators from AMD, they have 2 GCDs on each of them, graphics compute dies. But as a programmer, if you go onto the system and you try to query to see how many GPUs you have available, it's going to tell you have 8 available. And so for all purposes as a programmer, you really do have 8 GPUs available to you. And so in our documentation and on this slide, we've called them GPUs instead. So I just don't want anybody to be confused if you've sort of beefed up on this and you see these called GCDs and I'm saying something else. So if I talk about those GCDs, I'll call them GPUs. And if I talk about the MI250X as a whole, I'll call it an MI250X. Sort of the best way I can think of to do it. So, okay, so this larger main light blue rectangle that you see up here, that represents the CPU. It's only bigger than the other components because it has these finer details to look at for the user. And so you can see the dark blue boxes. Those represent the physical CPU cores. So they're labeled 0 through 63. There's 64 of them. And each of those cores has 2 hardware threads associated with it. So following the same convention as the Summit slide. Let's see. So up top here we have our, there's 2 SSDs mounted on each one of these nodes. So you have about 4 terabytes of node local storage. You have 512 gigabytes of DDR4 that you can access at speeds of up to 205 gigabytes per second, so a bit faster than Summit's accesses. You can see these 8 physical cores here, 0 through 7, that share this L3 cache region. It's sort of this medium blue in between there. And so you can see that these L3 cache regions, which I believe in AMD terminology they call these CCDs, I think core compute dies. These are connected to a specific GPU over here, right? You can see this blue line connecting to GPU 4. 8 through 15 is connected to 5 and so forth, as you can see with those lines. And that's in AMD's Infinity Fabric. So that's CPU, GPU Infinity Fabric. And you can transfer data between those cores and that GPU at speeds of up to 36 gigabytes per second. Right, and we then have this GPU to GPU Infinity Fabric. And so each of those gray links have a speed of about 50 gigabytes per second peak. And there are different numbers of those between each one of these GPU pairs here that you see, right? So 2 GPUs on a common MI250X have 4 of these links in between them. So you can transfer data at 200 gigabytes per second peak between those 2 GPUs there. GPUs 4 and 5 can communicate with GPUs 2 and 3 through these 2 links connecting the 2 MI250Xs. And so that's 100 gigabytes per second that those can communicate. And then that's similar down here, right, going across. And then you have the rest of these lines here. These are just single links between each of the GPUs in those vertical lines and the X there in the middle. And so that's 50 gigabytes per second that you can communicate there. So it's definitely much more complicated than the old days of like Titan, where you had just one CPU, one GPU, and then you had the one speed in between. And it seemed complicated back then when we were first getting into GPU computing, but now it seems so simple. Right, what else to point out? Oh, right. An important difference about this system is that you'll see it's the GPUs that are connected to the NIC in this case instead of the CPUs. So one of the GPUs on each of these MI250Xs are connected to a separate NIC. And each of those NICs are 25 gigabytes per second bandwidth. So you have 100 gigabyte per second bandwidth total, node injection bandwidth into or out of the node. But you need to use the whole node for that. We've seen cases where people are doing some simple testing, trying to get started on the system, saying communicating with one MPI rank on each node, and I'm only getting 25 gigabytes per second, and that's because you have these 4 separate NICs, and so it doesn't really matter in production. Of course, you're going to use all of the resources on the system, but something that's a little bit different than our last system. Interesting fact, one cabinet of Frontier has a 10% higher HPL than all of Titan, and it does that using only 309 kilowatts of power compared to Titan's 7 megawatts. So it's a much more efficient system in terms of not only power consumption, but in floor space, as you can see down here at the bottom. Right? Those nodes I didn't mention, those are actually the racks is what I'm meaning to get to. These racks, these Olympus racks, I forgot to mention. These each hold 128 nodes. They're about 8,000 pounds, so these are big nodes, and they're very dense. So they're about 4 feet wide by 6 feet deep, and that's about the equivalent of 2 full-size pickup trucks that's packed in there. So. Interesting. And yeah, it supports up to 400 kilowatts of power. I mentioned on the next slide that that's used 309 during that test, but that's the provisioned power. And another thing I did not mention that I should is that not only are the CPUs and GPUs water-cooled in this system, but the DIMMs and the network cards are also water-cooled to try to be as efficient as possible. Right, this is a large chart. I tried to fit it all in one slide instead of 2. We've covered a lot of this, so I won't necessarily go over all of it in detail. I will make these slides available, so you can check them out on your own time if you want. Let me see if I can point out some important parts. We've mentioned the peak performance on these systems. The nodes, you can see looking at this column, or row, and this column here, you can see we've went from a CPU to GPU ratio of 1 to 1 on Titan that I just mentioned, 1 to 3 on Summit, so 2 to 6, but 1 to 3 for the sockets, and then 1 to 8 on Frontier. So we're getting much more energy efficient by using more GPUs for the compute. I think Summit was already maybe 98% compute was through the GPUs, so I don't know, I didn't calculate this one, but I assume it's a little bit higher. Right, we talked about the memory, but you can see here sort of this big difference in jumping up this available amount of memory on the systems, as well as weighting it more evenly with the CPUs, with the GPUs, right? Where before, 2.4 petabytes of DDR4 and then only 0.4 of HBM, and so now we've made that much more evenly because people on Summit are trying to make, and GPU computing in general, trying to have their data live on the GPUs as long as possible, right? The data transfers between CPU and GPU can be very costly and be a bottleneck in a lot of codes, and so there were times where there was some codes that wanted to make everything live on the GPUs, but just couldn't because there wasn't enough space there. And so now we've increased that to keep that, to allow for that sort of workflow. Let's see, so the CPU to GPU I did mention. So on Titan, this is the GPU bandwidth. So 250 gigabytes per second on Titan for the GPUs, 900 gigabytes per second on Summit. That's the GPU memory bandwidth to that HBM. And now on Frontier, that memory bandwidth for the for those GPUs is 1.6 terabytes per second. So much faster bandwidth. The interconnect between CPU and the GPU went from 8 gigabytes per second on Titan, 50 gigabytes per second on Summit, and 36 gigabytes per second on Frontier. So in total, though, there's still a lot of bandwidth between the CPUs and the GPUs. There's just more of them. Let's see, and I think we've covered everything else here at some point. So this just sort of outlines the programming environment. So this is a Cray system. So Cray built this system and has their Cray programming environment on the nodes. And so you have Cray, AMD, and GCC compilers. If you're familiar with Cray systems, right, that's the Prague Env, Cray, or GCC, that sort of thing. There's the Cray profiling tools, tuning and debugging tools, and as well as the Cray MPitch that's optimized for the AMD GPU Direct. There's also the AMD programming environment, so that's ROCm, and has support for both HIP and OpenMP GPU offload. In addition to these vendor-provided packages, the software that's on there, there's also components from other places in the community, right? ECP, of course, has done a lot of work over the years preparing some of these tools that you see up here, the software. So there's LLVM enhancements that they've put into for Flang, OpenACC, OpenMP, Cocos, Raja. There's a HIP LZ, which is support for HIP on Aurora with the Intel components, MPI, HPC Toolkit, PAPI, etc. There's lots of different tools there. I couldn't possibly fit them all in this slide. And then we, at OLCF, we have contracted a company called Siemens to give us some GCC enhancements so that it will allow for OpenACC on Frontier, because there's some folks who want to be able to use that on the system, and also enhancements for OpenMP and Fortran as well. Right, and then the programming languages and programming models you can see down here at the bottom. Just sort of shows what's available and which compilers they're available in. C, C++, and Fortran are all supported in all the compilers. OpenACC is, as I mentioned, supported in GCC. You can see the standards, or sorry, the specs that you have there that are complete. OpenMP, so that's available in all of the compilers to different varying degrees. So that's 5.0 to 5.2 specs, if you're familiar with that. HIP is available through Cray and AMD compilers, so you can compile with either one. And it also has these semi-automatic translation tools for translating your code from CUDA to HIP. So it's fairly straightforward, we found, from the people who are already on these systems. So, you know, if you're not familiar with HIP and you are familiar with CUDA, it's very similar, right? So you do a CUDA malloc, well, you do a HIP malloc instead, right? So it was really a way to make it easier for people who are already CUDA programmers to be able to switch over to use HIP without too much training there. But there's a Hipify tool that allows you to sort of go through and make those changes throughout your code. And we've given a recent talk on it. We have a Preparing for Frontier training series, and as part of that, we've given a couple HIP talks already. But there will be more trainings to come in that series. Cocos Raja, so these are available through all the compilers, and these are programming models that are meant to be more portable across systems. And then UPC is available with Cray and GCC. And so I probably should have pointed this out at the beginning of this slide, but you see at the bottom right where it says that these items are also available in green, are available on Summit as well. And that's for just kind of pointing out the transition that people will do, right? If you're a user on Summit and you're moving to Frontier, you can see that you have OpenACC, OpenMP, and HIP, and Cocos and Raja all available on Summit and also available on Frontier. And so you can sort of, it's what that training series I just mentioned is meant for, right? It's to help these folks who don't yet have access to any of the Frontier or pre-Frontier systems to start getting started on Summit. So if you want to use, okay. So if you want to use HIP there, you can start doing it. So this slide sort of shows where, or I'm trying to say this, it shows how we got to exascale based on energy considerations. So the bar chart on the right shows, basically it shows the energy or the provision power that you would need if you were to take our last 4 systems and just make them bigger to turn them into exascale systems, right? So you could have taken Jaguar, right, the CPU-only system, and just made it much larger, and then had it be, on paper, peak, 1 exaflop. And so this bar chart shows, if you take that 2.3 exaflop system and you raise it up to, 1 exaflop, you would need about 3 billion, or it would be about 3 gigawatts of energy to power it. And so I'll take a step back for a second and say that, in residential, your houses, apartments, that sort of thing, the power supplies, when you get charged for it, you get charged in kilowatt hours, right? So a kilowatt hour is a sustained kilowatt of power consumption for 1 hour, and you get charged for that. And in Oak Ridge, anyways, it's about 11 or 12 cents for that. And so if you change those units to be megawatt years instead of kilowatt hours, that's 1 megawatt of sustained power usage for a year. And that costs about $1 million. And so you can use that to talk, it's just a more appropriate units to talk about these systems. So we'll look at that now. So if we did what we said, and we took Jaguar and we made it into an exascale system, it would be about 3 gigawatts of power, which would be about $3 billion a year to power that. And so, that's just not feasible. The goal is that, if you spend $200 million on a supercomputer, that you don't spend more than that to power it. So this is already sort of out of reach, right? And remember, that was the fastest supercomputer in the world at that time. So it was the one that you would want to scale up to exascale if you could. And so it shows that it's just not possible, right? It's not feasible to do that. If we do the same thing for Titan, you'll see that it's much more efficient. It's using these GPUs, but still, $333 million a year isn't gonna be possible. So exascale is just not possible in 2009. It's just not possible in 2012. Summit is getting much closer. So if we up that to a 1 exascale system, you'd need 65 megawatts of power, and so that would be $65 million a year. We run them for about 5 years. So again, you're going to be above that mark. You'll be what, $360 million or something like that. So close, but not there yet. Frontier, on the other hand, now you'll see that I've taken Frontier, since it's a 2 exaflop system, and I've cut it in half, right? Because everything else on here was a 1 exaflop system, so I just scaled it down. Remember, it was 29 megawatts of provisioned power, so I've cut that roughly in half, so 15 megawatts. So $15 million a year for 5 years is now $75 million total, and now we're able to achieve exascale. And really, this is one of the main drivers toward that, and something that the vendors, the labs, the folks in the community really worked toward to make possible. So it's just a kind of neat way to look at this and see how we got here. And that is all of my slides. So I can answer questions if I have time.
Thank you. Yes, I do.
Okay.
Any quick questions?
Yes.
What do you mean by warm water cooling?
Oh, right. So it's about 30 degrees Celsius. And so that is just, it's not cooled water, right? So it's warm water in the area. We don't really need to cool it down to the very cold temperatures that we used, for instance. So Titan was an air-cooled system, and it used refrigerant to really cool the air as it came out, but it used very cold chilled water to recondense the refrigerant as it went through. In this case, we're using just warmer water. So that's what it means. And so being able to use the warmer water and doing it on all of the components really helps us be much more energy efficient, in addition to the fact that we have a 1:8 CPU to GPU ratio. Yes?
We have time for another question. Yep.
Sorry.
Yeah, sorry. Can you just comment on some of the programming models? Specifically, how are you programming the AMD GPUs? And then secondly, some of these heterogeneous programming models like SYCL, OpenCL, are those prevalent at all with your developers?
So we do have these programming models, right? So we have OpenACC. It's through GCC. It's not super optimized at the moment, but we're working toward that. OpenMP can be used on either NVIDIA or AMD GPUs. HIP can be used on the AMD GPUs, just like you can use CUDA on the NVIDIA systems. Cocos Raja, so these are all options on both Summit and Frontier so that people can prepare in that way. So if you're using OpenMP offload, for instance, it's pretty straightforward. You're already using it. You can move over to the system, and of course, you'll have to reconfigure your make files because you're pointing at different places, but you're able to use that just the same. And then HIP, as I mentioned, is really very similar to CUDA, so it's a fairly painless transition for people. There's some parts of HIP, there are some parts of CUDA that aren't necessarily, some of the later features that aren't supported yet in HIP, and so there's some places where you have to have a couple of if-defs in there, but otherwise it's been fairly painless to move over there.